Hello students, welcome to the lecture on determinants of a matrix, and after this lecture we will be able to learn the following objectives. Discuss the determinant of a square matrix, explain the properties of determinants, understand the minors, describe the cofactors, discuss the applications of matrices and determinants, explain the adjoint of a matrix, understand the expanding to find the determinant, discuss the inverse of a square matrix, understand consistent and inconsistent systems, discuss the system of linear equations. Let us start with a brief introduction to determinant of a matrix. We want to form a product by choosing n elements where A is at n by n matrix. There will only be one element from each row and one element from each column in this product. For example, if one element of the product is A21, then no other element in this product will be from row 2 or column 1. If the number of inversions is even, then the sign attached to the product is positive. If the number of inversions is odd, then the sign attached to the product is negative. Notice that we did not say that the product was positive or negative. We simply are determining whether the product will be added or subtracted.
So in this video, we're going to find the determinant of a 2x2 matrix. So let's start with this 2x2 matrix A. I generalized it and used letters instead of numbers, just so you can see the formula better. And the formula is the determinant of this matrix A is equal to A times D minus B times C. And notice how A times D is the red diagonal of this matrix, and B times C is the green diagonal of the matrix. So let's use this formula that I just showed you to find the determinant of this matrix B. And the determinant of matrix B is equal to A times D, which is our red diagonal. So our red diagonal are the numbers 3 and negative 6. I need to multiply these two numbers together, so that's what I'm going to do right now. I'm going to multiply 3 times negative 6. And we need to subtract B times C. And B times C is our green diagonal. Our green diagonal are the numbers 7 and negative 4. We need to multiply these two numbers together, so that's what I'm going to do right now. I'm going to multiply 7 times negative 4. And now the only thing that we have left to do is multiplication and subtraction. So the determinant of our matrix B is equal to 3 times negative 6, which is just negative 18, minus 7 times negative 4, which is negative 28. So the determinant of matrix B is equal to negative 18 minus negative 28, which is equal to negative 18 plus 28, which comes out to positive 10. And before I finish this video, I want to tell you what the determinant is actually used for. The determinant is very useful in finding the inverse of a matrix. However, if the determinant is equal to 0, then the matrix has no inverse, or you could say that the matrix is not invertible. So since our matrix B has a determinant of 10, 10 is not equal to 0, so our matrix B is invertible.
Let us understand the determinant of a square matrix. The determinant of a square matrix is the sum of all the n possible signed products formed from the matrix using each row and each column only once for each product. The sign to be attached to the product is the same as the one determined by the formula minus 1 n when n is the number of inversions as described above. We generally do not compute the determinant by the definition, but it is good to know why the shortcuts that we learned at the beginning of the chapter are valid. The determinant is also a good example of an abstract idea that has very important practical uses. Students, now we will talk about the properties of determinants. The determinant is a real number. It is not a matrix. The determinant can be a negative number. It is not associated with absolute value at all, except that they both use vertical lines. The determinant only exists for square matrices 2 by 2, 3 by 3, n by n. The determinant of a 1 by 1 matrix is that single value in the determinant. The inverse of a matrix will exist only if the determinant is not 0. Determinant I suffix n is equal to 1, where I suffix n is n into n identity matrix determinant. A to the power of t is equal to determinant A. Determinant of A minus 1 is equal to 1 by determinant of A. Let's talk about minors. A minor for any element is the determinant that results when the row and column that element is in are deleted. The notation Mij is used to stand for the minor of the element in row I and column j. So M21 would mean the minor for the element in row 2, column 1. Consider the 3 by 3 determinant. I have included headers so that you can keep the rows and columns straight, but you would not normally include those. We are going to find some of the minors. How to find the minor for R2C1? The minor is the determinant that remains when you delete the row and column of the element you are trying to find the minor for. That means we should delete row 2 and column 1 and then find the determinant. See on screen. As you can see, the minor for row 2 and column 1 is M21 is equal to minus 4. Let us discuss about the cofactors of determinant. A cofactor for any element is either the minor or the opposite of the minor, depending on where the element is in the original determinant. If the row and column of the element add up to be an even number, then the cofactor is the same as the minor. If the row and column of the element add up to be an odd number, then the cofactor is the opposite of the minor. Sign chart. Rather than adding up the row and column of the element to see whether it is odd or even, many people prefer to use a sign chart. A sign chart is either a plus or minus for each element in the matrix. The first element, row 1, column 1, is always a plus and it alternates from there. See on the screen sign chart for a 2 by 2 determinant. See on the screen sign chart for a 3 by 3 determinant. Matrix of cofactors are, again, if all you are trying to do is find the determinant, you do not need to go through this much work. The matrix of cofactors is the matrix found by replacing each element of a matrix by its cofactor. This is the matrix of minors with the signs changed on the elements and the positions. Here we will discuss about expanding to find the determinant. Here are the steps to go through to find the determinant. Pick any row or column in the matrix. It does not matter which row or which column you use, the answer will be the same for any row. There are some rows or columns that are easier than others, but we'll get to that later. Multiply every element in that row or column by its cofactor and add. The result is the determinant. See on screen. Here we will expand our matrix along the first row. From the sign chart, we see that 1 is in a positive position, 3 is in a negative position, and 2 is in a positive position. By putting the positive or negative in front of the element, it takes care of the sign adjustment when going from the minor to the cofactor. Let us discuss about the applications of matrices and determinants. Area of a triangle. Consider a triangle with vertices at x1, y1, x2, y2 and x3, y3. If the triangle was a right triangle, it would be pretty easy to compute the area of the triangle by finding 1/2 the product of the base and the height. However, when the triangle is not a right triangle, there are a couple of other ways that the area can be found. Heron's formula. If you know the lengths of the 3 sides of the triangle, you can use Heron's formula to find the area of the triangle. In Heron's formula, S is the semi-perimeter, 1/2 the perimeter of the triangle. See formula on screen. Problems with Heron's formula include must know the lengths of the sides of the triangle. If you do not, then you have to use the distance formula to find the lengths of the sides of the triangle. You have to compute the semi-perimeter, so chances are you will have fractions to work with. Lots of square roots are involved for the lengths of the sides of the triangle and for the area of the triangle. It is not the easiest thing in the world to work with. Geometric technique to find triangle area. The triangle can be enclosed in a rectangle. The vertices of the triangle will intersect the rectangle in 3 places, forming 3 right triangles. These triangles are denoted A, B and C in the picture. The area of the triangle we desire will be the area of the rectangle minus the area of the 3 triangles. The legs of the 3 triangles can be found by simple subtraction of coordinates and then used to find the area, since the area of a triangle is 1/2 the base times the height.
Adjoint of a matrix. The concept of adjoint is defined only for square matrices. If A is a square matrix, then the adjoint of A is defined as the transpose of the matrix obtained by replacing the elements of A by their corresponding cofactors in det A. The adjoint of A square matrix is denoted by adjoint A. To find the adjoint of a square matrix, replace all its elements by their respective cofactors and then find its transpose. For example, if matrix A has elements A11, A12, A13, A21, A22, A23, and A31, A32, A33, then replace each of the elements by its cofactors as shown. Now we need to find the transpose of matrix of cofactors. This is done by writing the rows of the matrix of cofactors as columns to form the adjoint of the given matrix as shown. So we get adjoint A. Now, try out this simple problem on a 2 cross 2 matrix and find its adjoint. find the adjoint of the matrix -1, 5, 3, -2. To find adjoint A, we need to first find the cofactors of -1, 5, 3, -2.
Minor cofactor of a matrix minus the number determinant of A. I is a relative complement of J, is called the I, jth minor of A. We write Aij is equal to determinant of A, I, j. The I, jth cofactor of A, denoted Cij, is the number -1 is multiplied by I and added in next. Let us see on screen. Here we will discuss about inverse of a square matrix. The inverse of a square matrix A with a non-zero determinant is the adjoint matrix divided by the determinant. This can be written as, here A inverse is equal to 1 by determinant of A and multiplied by adjoint of A, or adjoint of A is divided by determinant of A. The adjoint matrix is the transpose of the cofactor matrix. The cofactor matrix is the matrix of determinants of the minors Aij multiplied by -1i plus j. The I, jth minor of A, is the matrix A without the ith column or the jth row. Now we will talk about consistent and inconsistent systems. When you solve a system of linear equations, what does your solution set, all of your solutions, describe geometrically? In each problem involving 2 by 2 matrices that we solved, our solution set was the point of intersection of the two lines represented by the equations in our system. In each problem with 3 by 3 matrices, the solution set was the point of intersection of 3 planes. However, a system of linear equations does not always have a point as the solution set. If you solve the system, let us see on screen. Here, x1 plus 2 by 2 is equal to 4. Here, 2 by 1 plus 4 by 2 is equal to 8. Here, 2 into 1 plus 4 into 2 is equal to 8. Algebraically, what do you get? You have an infinite number of solutions along the line. x1 is equal to 4 minus 2 into 2, because any solution to the first equation also solves the second equation. Therefore, you can choose any value for one of the variables and you will be able to find a value for the other variable so that both equations are satisfied. This is called a consistent system because there is a solution. A system is inconsistent if there is at least one solution. A system is underdetermined when there are an infinite number of solutions. Let's discuss about the system of linear equations. In mathematics, a system of linear equations is a collection of two or more linear equations with the same set of variables in all the equations. In other words, we can say a system of linear equations is nothing but two or more equations that are being solved simultaneously. Mostly, the system of equations can be used by the business people to predict their future events. They will model a real-world situation into system of equations to find the solution and manage their business. The solution of a system of linear equations can be of three types: one solution, infinite solution, no solution. Now, in the end, let us summarize what we have learnt in this lecture. To form a product by choosing n elements, where A is an n by n matrix, there will only be one element from each row and one element from each column in this product. If the number of inversions is even, then the sign attached to the product is positive. If the number of inversion is odd, then the sign attached to the product is negative. The determinant is a real number. It is not a matrix. A minor for any element is the determinant that results when the row and column that element is in are deleted. The inverse of a square matrix A with a non-zero determinant is the adjoint matrix divided by the determinant. A system is consistent if there is at least one solution. In mathematics, a system of linear equations is a collection of two or more linear equations with the same set of variables in all the equations.